Okay, here the recording in progress. Okay, so we're down to just 11.11. I've already done some. It won't take me long to finish. So I'll do some 11.11. I may sneak in a few review questions here and there. Okay, so I apologize. A lot of what I'm going to say right now is repetition. You've heard this all before, but that's just to catch everybody, to make sure people don't have an excuse. They say, oh, I don't know when was a test. I don't know when was the final exam and all that kind of stuff. Okay, so reminder, exam is Thursday, not Friday. Okay, so what's going to happen Friday? It would just be an office hour. You can come or not. I won't record Friday, and if you want to show up and ask questions, you may, but you don't have to. So the usual rules apply for exams. You submit all of this homework Thursday, 70% requirement. Again, that's very easy to do considering I do a great percentage anyway. And let's see. So questions are just like the homework, as I said before. Then all we have left is the final exam. Our final exam is Friday the 17th, 8:10 to 10:40 a.m. You have 2.5 hours. Okay. Most likely for the final exam, I'll pick 3 questions from every exam. So 3 times 5 is 15. So expect a final exam of roughly 15 questions. Okay. And I do have office hours during finals week, Tuesday, Wednesday, Thursday. Same Zoom link from 8:10 to 10, Tuesday, Wednesday, Thursday, but not Monday. Monday, I'm giving another final exam. Okay. And I don't promise I'll give you back your individual exam Friday or that weekend, but you will get the solutions video. And after the test on Thursday, my suggestion is to review 1 test a day. So Friday, review the first test. Then the following week, Monday, Tuesday, Wednesday, Thursday, test 2, 3, 4, 5. Okay, go over the videos the day after, right? I always give the videos the day after. So the video for Saturday, September the 4th will be the first exam. Saturday, 9:25 for the second exam. Saturday, 10:16 for the third exam. Saturday, 10:30 for the last exam. And then we haven't had the 5th exam, but you'll get it Friday. And that's how you study for the final exam. You're going to have 5 formula sheets, 1 from each previous test. Okay. If you still have those same cheat sheets, just bring them all. And if you want to add to them, you're allowed to add to them. Okay. So that's what's happening. And then before you know it, we're done. Okay. So very short time, Friday the 17th, you'll be all finished. And everybody enjoy the holidays, hopefully. Okay. All right, so any quick questions from those of you that are here? Obviously, if you're not here, you can't ask any questions, I guess, now. You can always email me. So any quick questions from people that are here about what's happening and so forth? Okay, so I'll lecture. It'll probably be a short lecture today and tomorrow and Wednesday. And then we have the test. And then Friday's optional. You can come or not come. All right, so let's get back to where we were. Yeah, reminder, bring polar graph paper for the final exam. It's not a promise that I'm going to give you to you, but you have to be ready in case I give you a polar question on the final exam, right? Okay, so getting back to some of the problems at the very end. So the 13 to 21 type. Okay, find the Taylor polynomial. We've already done that. But now part B, use Taylor's inequality to estimate the accuracy, right? So doing some of those types. Okay, 17. F of x is secant x, a equals 0, n equals 2. That means you're centered at 0. That's our best case. That's called a Maclaurin series. And x is between negative 0.2 and 0.2. Okay, so you know how uncomfortable secant function is to most of us, right? We don't like secant. Can I replace it with a polynomial? In this particular case, a quadratic, right? So I like quadratics, parabolas better than the secant function. Okay, very quick review. Secant near x equals 0 looks something like that. Almost parabolic. Tangent looks something like this near 0. Okay, this is going to help me in a second when I come up with the approximation. Okay. Okay, n equals 2. That is a quadratic. But when I use Taylor's inequality, I need the third derivative, which is actually clumsy. Okay, so the function is secant x. F prime is secant x tangent x. That's not too bad. F double prime does start to get kind of bad. So first times derivative of the second, product rule, secant x times secant squared x, plus second tangent x times derivative of the first, secant x tangent x. Clean it up, secant cubed x plus secant x tangent squared x. This is all I need just to get the Taylor polynomial. Okay, in this case, it's the Maclaurin series. But for the remainder theorem, Taylor's inequality, I need the third derivative. So that's kind of clumsy. So what's the derivative of this, f double prime? So 3 secant squared x times the derivative of secant x, which is secant x tangent x, plus, and then to differentiate this, it's a product rule. First times the derivative of the second, secant x times 2 tan x times the derivative of tan x, which is secant squared x, plus second function tangent squared x times the derivative of the first, derivative of secant x is secant x tangent x. Okay, clean all this mess up. This is 3 secant squared, 2 secant squared tangent, plus secant x tangent cubed x. These two combine to be 5 secant cubed x tangent x plus secant x tangent cubed x. Okay, big mess. Okay, so T2, Maclaurin series. Okay. By the way, quick word. You probably noticed when I'm having you write these series, I haven't been having you do the summation notation, which a lot of you were doing on the quiz. Unfortunately, that showed me that you weren't paying attention to the videos. You got help elsewhere or online or whatever, but I don't want the summation notation. I want you to write out the terms like so. Okay. Oh yeah, and another reminder, you should have gotten an email back from me about the quiz, and I emailed you your answers and a solutions video. Because remember, the ground rules are you've always got to do a problem like done in class, not some other way, even though on a lot of the quizzes I say it's open everything, you can ask for help. Yeah, but you have to do it the way we do it in class. Okay, and the same goes for this test and the final exam too. Anyway, so right now, I already know because of this and this, and I'm not even showing you the rest. It's going to be x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial. And that's already set. The E and the F part of the Maclaurin series. So that's back on page 760, box number 7. Okay. Only they ask for a polynomial, so I don't put the dot, dot, dot. Okay. So x to the 0 over 0 factorial set in stone, x to the 1 over 1 factorial set in stone, x squared over 2 factorial set in stone, the E and the F exponent factorial. Okay, and what I need to establish are the D's. So I just plug in. Quick reminder from trig, secant of 0 is 1. Secant is the reciprocal of the cosine. Cosine of 0 is 1. Reciprocal of 1 is 1. Secant looks something like this. Near x equals 0. Tangent looks like this. Tangent of 0 is 0. Okay, so I plug in 0, 1. Plug in 0, tangent of 0 is 0, so that's gone. Plug in 0 here, that's gone. This is gone. That's going to be 1 cubed is 1. Okay, so 1, 0, which means forget about this, 1. So the best quadratic approximation to the secant function is 1 plus 1/2 x squared. Okay, and if you draw 1 plus 1/2 x squared, okay, seems reasonable. Parabolic, opening up. Now we know secant does a lot of this stuff. It goes up, down, up, down, up, down, up, down. So after a while, Of course, it doesn't look like 1 plus half x squared. But when I'm near x equals 0, it looks pretty close to it. Now, for the absolute value of R2, the remainder. Okay, so the game we're playing is we're cheating. Instead of using the actual secant function, which people don't like in general, I'm going to cheat and use 1 plus half x squared. You say, well, that's not fair. That's a different function. Yes, but I want to find out what's the maximum error if I use this instead of this, if I'm between negative 0.2 and 0.2. So that's where you go to the third derivative exponent factorial. Okay, so third derivative was here. Third exponent, x cubed, x minus 0 cubed over 3 factorial. Okay, so I'm not actually going to plug it in. I'll tell you what to do. But based on this picture, okay, here's 0, negative 0.2, 0.2, negative 0.2, 0.2. It says between negative 0.2 and 0.2. How would I maximize the secant function? Well, 0.2 or negative 0.2. How would I maximize the tangent function? 0.2. Okay, so your task is to plug in 0.2 everywhere. Here, 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 and here, and here, and divide it by 6, 3 factorial, and that'll be your answer. Okay, so I didn't want to take up class time before that. Let you work that out, but you can punch that all in. And one other thing to keep in mind, your calculator probably doesn't have a button for secant. You'd have to do 1 over the cosine, right? So reciprocate the cosine for secant 0.2. Okay, so work this all out. So this is getting the third derivative exponent factorial. So this is Taylor's inequality, and you can use this anytime that it's applicable also. Okay. All right, so that was 17. Yeah. Okay, and now what I thought I'd do for now is 13, the actual 13. I think last time I gave you 13 star. Double check the text here real quickly. Yeah, this one. Yeah, I think this is a repeat. This is 13 star again. Sorry, this is not the actual 13. But I was asked about it. Okay, so square root function centered at a equals 4, n equals 2, between 4 and 4.2. Right here and right here, I know automatically it's going to be x minus 4 to the 0 over 0 factorial. X minus 4 to the 1 over 1 factorial. X minus 4 cubed over 2 factorial. Stop. Don't need the plus dot 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 because we're doing polynomials. Okay, so the function is x to the half. F prime is 1/2 x and negative half, which is equal to 1 over 2 radical x. Double prime is negative 1/4 x and negative 3 halves, or negative 1 over 4 x to the 3 halves. This is all I need if I just want a T2, but for the remainder, I need the third derivative, 3/8 x to the negative 5 halves. Plug in 4. Square root of 4 is 2. 1 over 2 times 2. Negative 1 over 4. 4 to the 3 halves. 4 to 3 halves means square root of 4, 2. Cubed is 8. 4 times 8 is 32. Okay, so 2 goes there. 1/4 goes there. Negative 1/32 goes here. Clean it up. Yeah, anything to the 0 is 1. 0 factorial is 1. 2 plus 1/4 x minus 4 minus 1/64 x minus 4 squared. Stop. So the best quadratic parabolic approximation to this function is this. How good of an estimate is it? So that's where I have absolute value of R2 of x. The remainder, if I stop at the second derivative exponent factorial, it's less than or equal to, you go to the third derivative exponent factorial. Okay, so how do I maximize this? 3/8 x to the 5/2. Recall by the reciprocal rule, I make this the biggest when I pick the smallest number, right? There's an x in the denominator. By the reciprocal rule, the smallest number will make this thing the biggest. So I plug in 4 here. Then over here, between 4 and 4.2, what makes this the biggest? 4.2, right? If I plug in 4, you get 0. If I plug in 4.1, you get 0.1. It'll be the farthest when I pick the farthest number, 4.2 over 3 factorial. Okay, so just punch that in your calculator. But that's going to be 3/8 times 4 to the 5/2 times 4.2 minus 4 to the third, all over 3 factorial. That's the maximum error I would have between 4 and 4.2, where instead of using the original function, I replace it with this polynomial, this one right here. Okay, I'm going to go back and look at some previous problems some people asked before about. Okay, so this is a little mini review also. Okay. 11.1033, I was asked for again. I mean, we might as well review for the test while we're at it. So x cosine half x squared. Okay, so you don't need to write the summation stuff. In fact, I'll be stronger. I don't want you to do the summation stuff, right? Just write the requisite number of terms that I have. So here's cosine, x to the 0 over 0 factorial minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot. Cosine half x squared, replace that, and that. Erase, 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 put parentheses, 1/2 x squared, 1/2 x squared. So it looks like this. And yes, that's equal to 1. So I'll just change this to 1. And then notice instead of x, parentheses, half x squared. Erase, half x squared. Okay. So it's kind of clumsy, but it comes out to be, that's x to the 4th, that's x to the 8th, x to the 12th. Okay, that's going to be 1/4 times a half is minus 1/8. You can work this out. That's 1 over 16 times 24. It's 384. And this is what? 1 over 64 times 6 factorial, 720. Comes out to be 1 over 46,080. Now I just multiply by x. So if we multiply by x, that's x to the 5th, 9th, 13th. So there's my answer. So x cosine half x squared is x minus 1/8 x to the 5th plus 1 over 384 x to the 9th minus 1 over 46,080 x to the 13th plus dot, dot, dot. Okay, so ground rules, when you give an answer for me in general, unless there's a good reason not to, you give 4 terms minimum in your final answer. Okay. And yeah, you might look at this and say, that's not very nice. It actually is nice in that it's a polynomial, albeit infinite polynomial, but a top polynomial nonetheless. Very easy to differentiate, very easy to integrate. You look at this, you know, I don't like a whole lot about it, right? Got a cosine, a weird function here, and this. It actually, I mean, to differentiate this might be kind of clumsy. It can be done. Oh, the integration is actually going to be nice by doing a U substitution, right? Might as well review for the final exam while we're at it. A U substitution would make that not so bad. But anyway, here we go. Okay, quick rehash on that problem that asked for the cosine of 5 degrees. And I apologize, I didn't write down which problem that was. See if I can find that for you. Problem 49, 7.10. Excuse me. He asked for the cosine of 5 degrees. Whoops. 49. Cosine of 5 degrees, 5 decimal places. Calculator here, so I can double check what's happening. Let's see, what do we need degree mode for this? Okay, first change it to radians. Remember, the calculator likes radians, so if you got it set to degrees, it automatically changes it to radians. All right, use the formula for cosine, pi over 36. So plug into the formula, pi over 36 to the 0 over 0 factorial, yes, that's 1, minus pi over 36 squared over 2 factorial, plus pi over 36 to the 4th over 4 factorial, and this is already 5 times 10 to the negative 6 power. Okay, so let me try to show that to you. Parentheses pi over 36 to the 4th divided by 4 factorial, which is 24. Pi over 36 to the 4th divided by 24. It's already less than 0.00001. Okay. So by the alternating series estimation theorem, if you stop anywhere, the error is no more than the next term. This expression alternates. Terms decrease in absolute value, and they approach 0. Therefore, the series is convergent. If I stop anywhere, the error is no more than the next term. The next term is under 0.00001, which means all I have to do is add up these, 0.99619. Okay. Yeah, I know this is 1. So that was sort of like a problem I gave you in a quiz before. Let me just show you 1 minus parentheses pi divided by 36 squared divided by 2 factorial, which is 2. 0.9961922. So to 5 decimal places, I'm going to get 0.99619. Okay. And then just for fun, the cosine of 5 degrees. Wait, whoops. 0.99619. So notice the theorem holds. I had 1, 2, 3, 4, 5 digits the same. The 6th digit doesn't match, and it wasn't supposed to. Right? The alternating series estimation theorem says you want accuracy to within 0.00001. This is less than 0.00001. So all I need are 2 terms. 0.99619. And could it be that your calculator actually does, when it does cosine of or sine of whatever, it could just do this infinite series. Okay, so my calculator has a whole bunch of digits. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 digits. So you could wire the calculator to say, okay, I'll use this for the cosine. Once I get a term that's less than 10 to the minus 12 digits, then I stop and present the answer as those 12 digits. Or however many digits your calculator has, 7 digits, 8 digits, 10 digits. Then whoever wired it together said, by the alternating series estimation theorem, once I get a term smaller than 10 to the negative 10, or 10 digits over, then I can stop. Okay. So if you want greater accuracy, you say, well, what about all these digits at the end? Well, I stopped after just 2 terms. You could, of course, go as many terms as you want. Going from there. Okay. Okay, let's see. Question about 11.425. Does the series converge or diverge? Summation n equals 1 to infinity, square root of n to the 4th plus 1 over n cubed plus n squared. So here's my strategy. This is basically like n squared. For super big n, which is what's happening, right? N goes infinity. Ignore the 1, square root n in the fourth case, n squared. The bottom is n cubed. And something less significant. So what's n squared divided by n cubed? 1 over n. So I'm going to compare it to summation 1 over n. All right, so take the limit of the ratio. I'm doing the limit comparison test. Limit n approaches infinity of this thing divided by 1 over n. And multiply top and bottom by n. So this is limit n approaches infinity, square root of n squared plus 1 times n over n times n squared plus n. These cancel out. So now I have this. Divide top and bottom by n squared in red. So underneath the radical, divide by n to the fourth. This one, n squared. So underneath here, I have limit n approaches infinity, 1 square root of 1 plus 1 over n to the fourth, that approaches 0, over 1 plus 1 over n, that approaches 0. So I get 1 over 1, which is 1. Okay. So limit comparison test says when I take this ratio, if I get any positive number, not 0, not infinity, and not undefined, if I get any real number, then both series converge or both series diverge. Whatever happens to one happens to the other. What happens to summation 1 over n? Where to go? Well, that diverges because that's our harmonic series. Therefore, the original series also diverges by the limit comparison test, LCT. All right, so that was that one. Let's show you a quick derivation for the expansion for the natural log. It came from integrating 1 over 1 plus x. Okay, ignore the integral just for a moment. 1 over 1 minus a minus x. 1 minus a negative x is geometric. First term is 1. Common ratio is negative x. So 1 minus x plus x squared minus x cubed. Then you integrate both sides. And that's how this came out to be ln absolute value 1 plus x. But we dropped the bars because the radius convergence was 1. So integrate x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4 plus dot, dot, dot. Okay, then just an extra note. If you plug in 1, you get ln 2 is the alternating harmonic series. Put a 1, these are all 1, 1 minus a half plus a third minus a fourth. That was your alternating harmonic series, which happens to converge to natural log of 2, which is kind of interesting. Okay, all right. So that was some more problems from section 11, for which I'm almost done, and some review questions. And tomorrow, pretty much the same. I'll do some more review questions, but maybe finish up from 11:11. But otherwise, I think I'm done for today. Okay, so let me stop the share. Check to see if there's anything in the chat. Any questions, please? Otherwise, same thing tomorrow. I'll do some review questions, or if you have review questions, you can bring them up. And I'm pretty much close to being done. Okay, any other questions, please? For the exam, we have more problems because this section has a lot more topics. I'll probably still give 10 questions. Okay, although, you know, some questions fall under more than one category. So that's part of what you have to think about. So most likely still 10 questions. And yes, every section will be covered in some sense. Well, there's one section that was just a review. I think section 7 was all review. So, yeah. Okay, any other questions, please? All right, that'll do it for today, folks. So have a good day. Almost done. Hang in there a little longer, and we'll see you next time. Okay, bye, everybody.
Take care.